the slides. Okay, now that I shared my screen, there's some problem. Okay, this one, yes. Uh, okay, well, I wanted to show you some other things first, but then wait, let me share again the screen. Yeah, so I didn't put some contents as we mentioned. Some of you give me the feedback of putting more contents about ethics, so that's duly noted for next time. I also wish I put a bit more information about visualization. So we talk a bit about visualization when we said how to build and visualize a vector space model. And that can be useful for you guys to better understand your data, but also for explaining the insights that you get from the data to like a potential client. But then in terms of visualization, there are some interesting work that we have done in the past. And here's one. It was done by these two brothers, two Indian brothers that helped me apply sentiment analysis to Indian politics. And so here is a simple application of sentiment analysis to political forecasting. But what's nice about this paper that is also available at this link, predicting political sentiments of voters from Twitter, is how we visualize the data. So especially if you're talking to an agency or someone who's not tech savvy, it's important to have good visualization tools that can better show things like, for example, party-wise tweet distribution or user-wise tweet distribution, and more importantly, how different personas and users connect to each other. What are the interrelations between different users, user groups, and persona, political parties, and so on? So you can take a look at this paper if you are interested, particularly interested in data visualization, and there are many others. In general, the one thing that you can do is to have a library or a tool to visualize your vector space model. So in this other work that is also available on our website, we use that to visualize the relationship, how similar different countries are based on some specific features. So this is the the tools that you can use to visualize a vector space model actually can be very useful to better have an impression or an intuition of how similar or dissimilar different things are. So in this example here, we're talking about countries, but then this once again can be anything from documents, tweets, financial reports, images, videos, and whatnot. And so you can text me or send me an email later if you are interested in these topics that are more on visualization. But unfortunately, I'm not covering those in the course. So yesterday we talked about the suitcase model, and I want to start again from there. But first, I want to ask you guys if you have any questions about it. So first, we talk about the limitations and potential of large language models, but then we also talk about how a framework like this can be very helpful, not only for sometimes even improving the accuracy, but most importantly, to increase the interpretability of a system so that, as we mentioned, you can do a better error analysis and ablation study, and once again is also more cognitive inspired. So all these are the things that we discussed yesterday, and once again, each of these models can be a PhD on its own, or even like there are some people that they dedicated their whole career to just one of these modules, like a Lakoff that only worked on metaphor, and other people like maybe Andrew or Tony that only focused on emotion and personality. So again, it's too much to look at each of these in very much details, but that's why in the book we give a nice overview of what are the goals of each of these modules, and some data sets, some benchmark that you can use for training your algorithms, and also what are the state of the art in each of these NLP tasks. So first we looked at the syntactic layers, then we talk about the semantic layers. That was interesting to some of you, especially for word sense disambiguation. I forgot to share that paper where we applied neurosymbolic AI on word sense disambiguation, but I can share that with you guys later. And finally, we also talked about the pragmatics layer, which is maybe the most interesting one, where you're looking at more complex algorithms and techniques for metaphor understanding and personality recognition, sarcasm detection, not just from text, but also from different modalities. And finally, also aspect extraction that, as we discussed, it's very important in the context of sentiment analysis. And once again, it's not like you have to do aspect extraction all the times, because in some cases you may only have data that only is focusing on one aspect. Like, for example, if you have a whole data set that just talks about iPhone in general, you don't need to do aspect extraction. But when you have finer grain text and opinions like this one, where people talk about the specific aspects or features or opinion targets of like the iPhone, then you do need to do aspect extraction. Otherwise, you may get ambivalent results. And then again, we stress the importance of doing aspect extraction also for comparative evaluation. And this is extremely important for some businesses that are working with products and services that different people with different preferences use. All this focusing on polarity detection, because that's what we do in my group. But once again, you can replace this final module of polarity detection with anything else, including um, depression detection or emotion detection or even dialogue systems, whatever you guys are doing. So all this to come to the final chapter of this course, which is neurosymbolic AI. So neurosymbolic AI is about using a hybrid approach that uses all the state-of-the-art techniques in machine learning and deep learning together with other different techniques. And why is this important? Again, because it can reduce hallucination, and it can result in a model that is that you can trust more than just a statistical model. So it all starts from it's a suitcase model. You could say that is also goes along these lines, and this is something that we have refined over the years. And this again is part of the book that I published last year, but actually 10 years before, in 2014, we were already trying to do something similar. But this other paper from 2014 is still quite relevant and interesting, because it borrows the idea of jumping curves from business to to forecast where NLP is going in terms of what we are modeling with our NLP models. And so here the most important point of the of jumping curves in general, not just in this case, is that you cannot keep doing incremental um, progress on a specific topic that is very complex. So sometimes you really have to jump the curve. So change completely what you were doing. And that's exactly what happened in NLP. So initially, we were just focusing on making the bag of words model better and better with things like we discussed. We went from one hot encoding to better and better versions of TF-IDF, which has so many different variants. But then we were kind of stuck there until, as discussed, we got the insights from Mikolov, who took back the convolutional neural network from Jan LeCun and then started the revolution of deep learning in text mining and NLP. What's next? Maybe we need something that is also completely different, where we also look at something that is more cognitive inspired and is really trying to mitigate or solve the symbol grounding problem and visualize reason in a way that is a bit more visual, or at least that is more grounded, so that you can better perform narrative understanding. Because today, all these tools, deep learning tools, are very good for dialogue systems, question answering, even classification, but not so much for narrative understanding just yet. So with all this in mind, we came up with the latest version of ScientificNet. So ScientificNet is our own knowledge base for common sense and sentiment that you can freely download. We started this project back in 2010, and then every 2 years we have a new version. So we had ScientificNet 1 in 2010, ScientificNet 2 in 2012, and last year we publish Centicnet 8. We don't plan to go on forever with this Centicnet, so probably we'll stop at Centicnet 10. But the latest paper is quite interesting because we compare Centicnet with ChatGPT and other NLP models that are very good, like Roberta, as I mentioned, is still considered one of the best transformers models for NLP, and also Word2Vec, the continuous bag of word model, and also the bag of word model, TF-IDF, the term frequency, inverse document frequency that we briefly discussed at the beginning of lecture one. This paper is also interesting for those of you who were interested in word sense disambiguation. Part of the algorithm for building CentiNet A uses neurosymbolic AI for transparent word sense disambiguation. So it's a three-stage kind of normalization. So first we do all the things that we already discussed yesterday in terms of lemmatizing, stemming, removing of plurals, removing of stop words, case folding, and so on, to get to some sort of more general version of the concept or multi-word expression. And then from there on, we go one step further to try to come up with the conceptual primitive. So the idea of conceptual primitive is something that belongs to the umbrella of symbolic AI. Conceptual primitives were initially proposed by Richard Schenck, and the idea is that you have a primitive, like we already discussed when we were talking about symbol grounding, that represents all the possible ways of expressing the specific concept in English or in any other language, so that you can later on build a representation that is based on that, and hopefully, possibly, a representation that is language agnostic. And in this case, we do that by defining a sort of double transfer of ownership, where you have that the T minus one, money is with person or user A, the phone is with user B, and at T0, when the action buy happens, the opposite happens. So you have, again, a double transfer of ownership, to put it in Shank's terms. Again, as we discussed yesterday, and this is not something that you can do for every possible concept in English, because some concepts are too abstract to be represented in this way. And also, some even concepts that are not too abstract will be very difficult to be represented in logic or forms like this, because as we discussed, there could be other dimensions or variables at play, like the time dimension, or like when we said, like, I get something from someone. There's also things like, did I force this someone to give me this? Did I pay money? Was it a fair exchange? So it's much more complex, the problem here. But if you choose a relatively smaller and easier domain like sentiment analysis, you can attempt to do something like this. And if you do this, it's very good for different reasons, for disambiguating um, many of those multi-word expressions like you had here, that maybe depending on your training data set may be linked to different emotions or even different polarities. But if you have something like this, they can all be connected, and reasoning can happen only at the pragmatic stage, where you just assign a polarity or a set of emotions based on what's really happening there, what's the current state of affairs of the operating environment. And this has a lot of perks for classification, but also, again, for disambiguating all the possible ways that I can express the same concept in natural language. And again, as we discussed yesterday, this works for those words and concepts that are not too ambiguous, because then if we have different senses of the same word, we will need to have a different representation for each of those senses. But this is nonetheless quite interesting, because it's again an attempt to do something that is more like universal symbolism, like today we only have for very few things, like maybe mathematical symbols or musical notes. But if we manage to have something like this, at least for some of the domains and application, then this is something that potentially is also valid in all languages. Of course, every language and every culture will have different nuances, but if we focus on the representation rather than the words, then this is something that potentially can be done again in a restricted domain. So all this belongs again to the umbrella of neurosymbolic AI, which once again is what is using bottom-up data-driven approach like a large language model or a deep neural network, together also with top-down information that I can get, for example, through common sense knowledge representation and reasoning. And this is important for different reasons. Once again, if you only care about accuracy, you can just train a deep neural network or a large language model, and you probably get an accuracy that is good enough. But when you start talking about explainable AI and AI models that you can trust, then it's also good to have this other kind of approach that can verify what the large language model has produced in a kind of system one, system two architecture. We'll talk a bit more about this later. But I also want to mention that this is very much cognitive inspired, because also us humans don't really learn everything in a bottom up way, in a data driven way. Yes, we learn maybe a lot of the sentence constructions and the way we speak is coming up because of after learning, after hearing the same sentence structure many times, or even actions that we learn how to perform. It's based on trial and error or seeing someone doing that. But it's not like everything we learn it like that. For example, I don't learn that I shouldn't jump out of a window because I tried that before, or because, God forbid, I've seen someone doing that. So there are other things that we need to take into account beyond learning by example, and that's what neurosymbolic AI tries to do. It's also similar to the concept of panalogy or parallel analogy that we discussed before. It could be useful, for example, to have your data represented as a vector space model like the ones that we have discussed during this course. But then you can also have the same data represented as a knowledge graph or semantic network. And these two, even if they are the same data, they, because they represent it in different ways, they can be used for different kinds of reasoning. And also you can shift between one and other representation depending on what you need to do. So for example, in a the vector space model is very good for similarity. So as we discussed, you can calculate the cosine similarity between two data points to tell how similar these two things are. So if here I have a semantic network about food and I build a vector space model out of it using a matrix representation first, here in this vector space model, I can tell, for example, that cake is similar to dessert or similar to chocolate, similar to ice cream, because maybe for that specific reasoning step, that's what I need. I need maybe a lot of items that are similar to cake. But if in another case the question is more about what is a cake, and or maybe where can I find a cake, or how can I bake a cake, then maybe it's better to shift to this other representation where I can follow, for example, an is a link to see what a cake is and what is used for, which properties does it have, and so on. So that's in a nutshell how you can define neurosymbolic AI, but this is still a relatively young and upcoming research field. So different people will also have different definitions of what neurosymbolic AI is. So this is our own definition. This is how we do neurosymbolic AI in my group, and with particular focus once again on affective computing. So maybe all the things that I'm saying here will not be perfectly transferable to some other domain, but you can try, and I'm also happy to discuss about that or even work together on another topic. Another way that you could do neurosymbolic AI in a very simple manner is that you can use an emotion categorization tool, like, for example, the hourglass of emotions to perform polarity detection. So the simplest way to do polarity detection, as again, as we discussed many times, is what? I take hundreds or thousands of reviews. I I train a deep neural network on these, and then as a result, I have a neural network that can classify with a certain accuracy text as either positive or negative. But if you want to have something that is more interpretable and maybe even explainable, you can instead use an emotion categorization model like this, or like Ekman model, or Plutchik wheel of emotion, to then do what? To detect emotions from text and use these emotions to then calculate the polarity, maybe even based on emotion cause pairs. So understanding what are the causes of what emotions in a piece of text to then um, come up with the polarity value and maybe even a polarity intensity. So that's what the hourglass model is useful for. It gives you very fine grained information about emotions in terms of intensity, different types of emotion, different intensity, and how to calculate polarity based on these. I still have a few more slides about the hourglass model later, so I'll leave it here for now. But again, we can discuss more about this if you are interested. I want to conclude this topic of neurosymbolic with another funny metaphor. So throughout this course, I keep complaining about metaphors and analogies that then become beliefs. And here's another one. But maybe that's how you will remember clearly the difference between neurosymbolic AI and other kinds of AI. So this is a metaphor that I use, an analogy that I use when I introduce my undergraduate student to AI and neurosymbolic AI. So science is a magic that works. That's what I didn't say that, but it's a quote by Kurt Vonnegut, and it means that basically whatever works and works very well in sometimes in ways that you didn't expect can be considered as magic, especially in the case of black box models that you don't know exactly how they work. So whenever you get that wow factor, you could say that that is magic. So if we define AI as magic, then some symbolic AI or deep learning or machine learning, then it's maybe more similar to black magic. Why? Because it's very powerful, but we don't have much control on it. We don't know exactly, as we discussed when we were talking about neural network, what's happening in those weights and those links in between nodes. But the symbolic AI or old school AI, where I have those clear representations like the one here that we saw earlier, knowledge graphs, semantic networks, even ontologies, they're very transparent. They're not as powerful as deep learning because they have their own limitations, but at least they are very transparent because at any time I can take a step back and see why I got that kind of output, that kind of result by looking, for example, at spreading activation in the knowledge graph. So neurosymbolic is about putting these two together. It's about using the strength of statistical models together with knowledge representation. And this, there's not just one way to do this, of course. I told you with past examples how we do it, and I'm going to give you a few more examples in the next few slides, but it's a more general approach of how you can solve a problem. Once again, I want to stress that it's not like you have to use neurosymbolic AI all the times. If your final goal is only to increase accuracy, then it's maybe better to use a purely statistical approach. But when you are working with fail-safe application or applications that involve ethics or explainable AI, that's then when you should use neurosymbolic AI. Here's is an example from a kind of old paper from 2022 when we used symbolic representations, the knowledge graph of SentiGNet, to inject extra knowledge into a subsymbolic representation. So in particular, we built this graph convolutional neural network for aspect-based sentiment analysis. So what did we do? We trained this GCN on some um, aspect extraction and polarity detection, but then we also added in the form of embeddings some knowledge coming from SentiGNet so that, and we showed in the experiments that the new injected or enriched GCN works better than the standard vanilla GCN. Why? Because on top of having all the information that the GCN learned from the training data, you also have this extra knowledge coming from SentiGNet, which once again is also encapsulates some common sense knowledge. Another thing that you can do is the opposite. You can use a subsymbolic representation to build a symbolic representation. And that's what we did 4 years back, 5 years back with the SentiGNet, the version number 6 of SentiGNet. So here we were also looking at verb concept like buy, for example. And back then, we weren't using transformers much yet, so we were still focusing on recurrent neural networks. We were using bidirectional LSTM, so we used those to learn in how many ways in English you can express a concept like buying something, including like getting something for someone, purchasing someone something, and so on. And then we didn't use that directly for classification. We used all this information to build a knowledge representation, and which we were using then later on for classification. And what's interesting here, again, if you want to do this for every possible word in English, this becomes a formidable task. But if you're only focusing on a few primitives and on a specific domain, then this becomes more doable. So we had in SentiGNet 6, but also later on SentiGNet 7 and 8, this hierarchical structure where you have name entities and the bottom layer of the pyramid. If you see this in upside down, then these are linked to concepts. So for example, you have the concept of supercar, and to these are linked all the possible entities, name entities that fall under that category. Then you can go one level down and have the conceptual primitives that define each of these things. And finally, you have some super primitives that are those primitives that for which then you need to build some sort of semiotic representation using logic or using that universal symbolism that we discussed before. So this is very much inspired by semiotics, but also linguistics, and it works a bit like you do when, for example, in physics, you define speed in terms of time and space. So it's about breaking down meaning into simpler and simpler bits that then you can explain using some sort of symbolic representation. So once again, this is useful. Why? Because then when you have a multi-word expression like cooking something or making something, uh, you don't assign statistically a positivity or negativity to the expression. You go down one level to the reasoning layer and understand that generating something means that you go from a situation of the operating environment where this something doesn't exist to a new current state of affairs where this thing exists. So ultimately, the polarity of this multi-word expression is connected to whatever I have generated. If the thing that I've generated is connected to positive emotions, then the overall multi-word expression is positive, and vice versa. The same goes with the opposite. So if I terminate something, terminating X means that I go from a situation where X exists to a situation where X no longer exists in my operating environment. So if this X was something connected to negative emotion, something negative, terminating this negative thing actually result in a positive polarity. So this is really to understand the dynamics and the meaning that is rooted in all these concepts and multi-word expressions. Once again, I want to stress this works well for sentiment analysis and especially for those texts that are rather unambiguous. For other things that have for other domains, you will probably need something more. And also for those kinds of texts that contain sarcasm or multiple senses, then of course we need to be more careful. Hi, Vivek, please ask your question. I know that you like this kind of things.
Yeah, I actually like symbolism a lot because I'm also kind of trying to develop some predicate logic around some Hindi language,
Great.
some of the concepts of Hindi language. So I was quite interested in knowing what is the meaning of primitives and why they are called primitives, and how what is the difference between super primitive and primitives.
Yeah, thanks for the question. Again, here, primitives is a word that is used in different disciplines in different ways. So if you look at semiotics, linguistics, and computer science, they are mostly used with different nuances, same as semantics. When we talk about conceptual primitive theory by Schenck, we mean a more general um, form of, for example, different verbs that can be um, generalized to a more general form that is the one that is mostly used, or the simplest form, like we had in the previous slide, like we had that buy, purchase, pay for, and so on. They can all be generalized as buy, but that's actually just a label. Like we said, when we do clustering, we cluster different, like in this case, that's what we're doing as well. We're clustering different ways to express the same concept in a multi-dimensional vector space, then we have to put a label on this group of verbs or words that mean the same thing. And so we pick the one that is more common, like by in this case, but that's again just a standard. So that you can have different levels of primitives, and then at some point you have to stop. So when you get to a primitive that can no longer be generalize into another primitive, that's when you have a super primitive, and that's when you have to ground this primitive with some sort of meaningful representation. So, for example, here you can have a lot of concepts that are synonyms, and they are connected with the concept of generating something. It can be cook up something, invent something, create something. And so I can represent all these concepts with the primitive that I call generate. Is generate a super primitive? No, because it can also be explained in terms of another primitive exists. Is exist a super primitive? Probably yes, because I cannot really generalize it with another primitive, so I have to come up with some sort of logic or symbolic representation for it. But again, um, this is not a universal truth. So depend on what kind of data you're working with, and what are you ultimately interested in. For us, exist is a super primitive because then we have a representation for it, and that's what ultimately we need to define the polarity of something happening, including all the other primitives that are built on top of this super primitive. But there is no formal definition. So I'm mostly referring to conceptual dependency theory by Schenck, but again, this is still a matter of debate in both semiotic but also psychology and computer science on how to effectively and universally define a primitive. And the same actually is happening also for emotions. Believe it or not, there is still not a standard way of representing emotion. There's no consensus even among psychologists on what an emotion is, even if you could talk about basic emotions. And one example, as I'll talk later, is the emotion of surprise, which some say that it's not an emotion, some say that it is an emotion. So here you have to take this with a pinch of salt. This is how we do it based on some literature, but it's not all the literature say that this is the way of doing things.
Thanks, Eric. That was really insightful for me to learn. And one last question related to this. Suppose
Mhm.
you define any super primitive, okay? Um, is there any parameter of deciding what and how that super primitive will take its own arguments? So, is there any kind of parameters of deciding what counts as an argument for that super primitive?
So first, it depends on what you're doing and how you define that super primitive. So, for example, I've been part of some simple projects where people were trying to build a semantic hierarchy only based on the is a relationship. So you can just throw as much data as possible into a knowledge graph, and then all these nodes inside are only connected by is a. So it's slightly different from what we've seen here. Here, normally in a semantic network, you have many different properties. But if you only focus on an is a property, then you kind of have this automatic hierarchy. Why? Because then among all these concepts, there will be some that will only have inward um, links and no outward. So you can define, for example, one way of defining a super primitive is based on that. If it's a concept, it's a node in my semantic network that is only receiving links and doesn't have any outward link, that's a primitive. Then how do you define this primitive? That pretty much depends on what is the thing that you're doing. So yesterday, for example, we defined primitive generate x, like going from not x to X, but it could be a different definition based on what you're doing. So there's no really ultimate answer to your question. You can do something like this, a universal symbolism, or do something like first order logic to define how to go from one state to another. If you take a look at conceptual dependency primitive and theory by Shank, you'll see that he also do this in another, in yet another different way. So it depends on what you need and what is the final application. There's not just one way to define this, but it's a two-phase process where first you have to identify the primitives, and second you have to ground them in some specific um, meaning representation. For example, a primitive could also be simply an emotion, and then the way that you define this emotion can be through an emotion categorization model like this. So your super primitive, if you're only interested in emotion detection, could be the list of emotions that make up your emotion categorization model. And then you have the model itself to decide how to work with primitive and how each primitive or emotion relate to each other, which ones are positive, which ones are negative, and so on.
Thank you, Eric, for your detailed explanation. It clarified my doubts perfectly.
Yeah, I'm sorry I cannot give you a more definitive explanation, but yeah, this is how we do it. But if you're interested in this, yeah, please read. I can give you some references. Definitely, you have to read Conceptual Dependency Theory by Schenck, but there are other works that were done mostly by linguists. So all these people that worked on semiotics and primitive conceptual primitives were mostly linguists and psychologists. But I think that we still can use a lot of this work for the next stage of AI.
Mhm.
Okay, so we can continue. I don't know, maybe we can have a few more slides and then we take a break. Um, so the reason why we are doing all this neurosymbolic AI, once again, is not because we want to increase accuracy, but because we want to have a framework that is more transparent, more explainable, more cognitive inspired. And once again, because word embeddings are very good mostly for representing knowledge in a way that I can make those comparisons that we talk about. So this slide here maybe encapsulate all the things that we discussed in lecture one when we were talking about data representation and reasoning. We can have words that we represent as word embeddings. As we build these word embeddings, we have bigger and bigger embeddings. We can use a dimensionality reduction technique like TSVD or random projections to project all these huge embeddings into a smaller space that can be 300 or 100 dimension. In this extreme example here, we go from we project into two dimensions only, and that's also doable. Like if you only happen to have just seven dimensions, like we had in the first example about the plays of Shakespeare, you can also do an SVD and and take only throw away five of the singular values in the bottom right corner of the sigma matrix, and you're left with what? You're only left with the first two singular values from the top left corner. And so if when you plot those, when you visualize those, you have a beautiful two-dimensional space like this. And but then the question here is, what can you do with this space? And this space is useful for uh, calculating the similarity between these data points, concepts, documents, novels, images, videos, and whatnot. So I can calculate the Euclidean distance or the cosine similarity between these 2 points, but that's pretty much what I can do. So a vector space model and word embeddings in general are good for calculating similarities only. But here, nowhere in this slide, I have grounding of the meaning of any of these anywhere. So, for example, if I know what is a man, because I have the definition of man in some sort of logic or semiotic form, then this vector space is very useful because I know that woman is similar to man, and king is also similar, and queen also to a certain degree it's similar to man. But if I don't have this grounded anywhere, then I don't know what I'm talking about, right? So for us, this is quite intuitive. Why? Because we know English. But think, for example, if I show you these images in a language that you don't know, like Cyrillic or Arabic or Burmese, then these points with some characters associated with would mean absolutely nothing to you. And that's pretty much how a vector space model. We have these data points that we associate to some semantic concepts in our brain because we have the symbol grounding solved. But a vector space model doesn't have that luxury. So all it can do is to understand, is to, for example, calculate the similarity to see which data point is similar to which other, or do clustering to understand that, for example, dog, cat, and kitten are different from houses. So this can be used also for classification, but that's pretty much it. I don't have anywhere in my vector space model the definition of a dog and or some sort of representation of a dog. So that's maybe in one slide here explain why we need neurosymbolic AI. Again, sorry to repeat myself so many times, but if I'm only interested in classification or clustering, I don't care about neurosymbolic AI. Why? Because I'm happy enough to represent data this way, calculate cosine similarity or Euclidean distance, and do clustering or classification. Who cares what a dog or a cat is if you can effectively do classification or clustering? This is important for more complex kinds of reasoning where you really need to know what you're doing and what are these data points or entities that you're working with. And this is yet another slide that shows you the same thing. So here, with these vector space models or embeddings, you can very effectively compare what is similar to what, but there's no answer to what is what. But that's why using these two together is powerful, because then once again, if I have a grounding that tells me what a man is, then I can also somehow explain what the rest is based on this similarity. So I hope I convinced you that it's interesting to at least look at neurosymbolic AI, and I already convinced Vivek, but I hope I can convince more of you. But yeah, I think we can take a we can take a break now, and if you have more questions, then maybe you can ask me later.